Okay, so I am going to draw some stuff which will help you understand how osmosis works. So I'm doing this on my iPad, so not the best artist in the world, but we'll see how it goes. So let me open this app and let's take a new blank screen. Thanks, Eddie, go away. Okay, so let's just get a pen going here. Good. Okay, so we're going to put down the middle here a selectively permeable membrane, and this is, I'm just drawing some gaps in here to show you that this is selectively permeable. And so that means that certain things can pass and certain things can't. So is what we're going to do is we're going to have this membrane in the middle here, and that membrane is going to allow water molecules to move back and forth freely. So water molecules can go back and forth across this membrane, and that's totally fine. It's just going to let water move. And what we're going to do next is we're going to put some solute molecules. So I'm just going to let's just do sodium. So let's just put some sodium ions down on the left side of the membrane. I'm just going to put 5 on the left here, and then we'll put some more on the right. So let me just draw those in. One, 2, 3, 4, 5, 6, 7, 8, 9. Let's just put another one here. Okay, so the left is going to be, remember, hypotonic, and the right over here is going to be hypertonic. So, okay, so set the situation where hypotonic on the left and hypertonic on the right. Now, these are obviously sodium ions, and so they're dissolved in water. So what does that mean when we say something's dissolved? So when something's dissolved, is what we're going to have is the water molecules, and I'm just going to draw the water molecules like this, and then I'll make them a little abbreviated. So the big ball there is the oxygen, obviously, and that's got a slight negative charge on it. I'm just going to put a little negative dash by that so you don't forget. And then the two little balls are hydrogen atoms. And so when something dissolves, it gets covered in this shell of water. So I'm not going to draw all of these in because that's kind of annoying, but what I'll do is I'll draw these kind of dots to represent the water molecules completely surrounding the sodium. So let me just kind of draw those in quickly. The actual number, the absolute number is not important here. So on the left here is what we see is we've got a certain number of water molecules which are surrounding the sodium. So, I mean, let's just count them up. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 16, 17, 28, 29, 30, 46 or so, 46, 47 water molecules surrounding these 5 sodium ions. Now, if we look over on the right hand side in our hypertonic solution, let's just do the same thing. And so I'm going to draw these in, and I'll stop talking, and I'll speed this up so you don't have to watch me doing this. Okay, so now is what you see, just comparing these, you can count them all up on the right if you like, and I don't know how many there are, but I mean, I'm just going to estimate and say there are about 100 water molecules surrounding the sodiums on the right. So what you see is that on the right, there are more water molecules associated with the sodium, and remember that's going to be like a hydrogen bonding interaction, more water molecules associated with the sodium on the right than there are on the left. So if we just think about like a little graph to represent the different amounts of water that we have on each side, in terms of the total amount of water, it's the same on each side. So the same total amount of water on the left as there is on the right. So the total water is the same on each side. But on the right-hand side, more of the water molecules are associated with the sodium than they are with the sodium on the left. So that means that if the sodium can't move, and so the sodium is kind of blocked from moving because it's too big, And so the sodium can't move, and the sodium on the left can't move, so it's blocked from moving. But any water molecules associated with that sodium also cannot move. So on the right, we've got 100 water molecules which aren't able to move, versus about half of that on the left. So what we set up is that we end up with more free water molecules. Free water molecules are the ones which can move back and forth across the membrane. So those are the ones which aren't associated with the sodium. So let's just do some math here. Let's just say that there are, this is a silly example, but it makes it easier. Let's say there are 500 water molecules in total on the left and 500 on the right. Now if we take off 46, that leaves us with 454 water molecules that are free to move on the left. Now over on the right here, we've got 100, and now we've only got 400 water molecules. So this means that there's more water on the left than there is on the right in terms of the free water. That means there's a higher concentration of water on the left, and if I just erase some stuff down here, there's more water on the left. So if we draw something that kind of represents, pens change color. Okay. If we draw something that represents this much water on, so this is free water on the left, and then we've got this much free water over on the right-hand side, water's going to move, have the net direction of movement of left to right. Now you can memorize that. I mean, if that's what you want to do, you go ahead and do that. But we're always going to have water moving from hypotonic to hypertonic. Now you can memorize that, but when I give you different examples of this on quizzes and things, you need to be able to explain why water moves from hypotonic to hypertonic. Now, if we let the solutes move, then the sodium will end up equilibrating across the membrane, and there'll be no net movement of water. There'll be no diffusion, because we eventually just means that we have the same free water concentration on each side. So that is my quick explanation of why water moves from a hypotonic solution to a hypertonic solution. And we'll talk about this again in class.